Welcome to the Explainer. If you're someone who loves to crack open complex systems and really see how the gears turn, you are absolutely in the right place. Today, we're going to build a practical, totally math-grounded machine learning tool belt. We're moving way past the buzzwords to understand exactly how algorithms discover hidden structures in raw data, entirely without human guidance. We're going to roll up our sleeves, dig into the actual math, look at the formulas, and see exactly how the machine thinks.
Okay, let's just quickly glance at our roadmap. We'll start with the unlabeled data puzzle, move into clustering with k-means, explore dimensionality reduction via PCA, catch some anomalies with isolation forest, and finally, we'll put all these tools together into a real pipeline.
All right, kicking things off with Section 1, the unlabeled data puzzle, discovering unknown structure.
Imagine you run an online store. You've got this massive, messy database filled with thousands of rows of customer behavior, right? Monthly spending, number of visits, average order value. But here's the catch. There's no correct answer column. There aren't any predefined labels telling you who is a frequent buyer or a discount shopper. This is what we call unlabeled data, and finding the unknown structure within that data is the whole point of unsupervised learning. Notice the really clear contrast here. Supervised learning relies on correct answers to predict known labels, like cancel or stay. It's honestly like taking a test where you literally have an answer key to check your work. Unsupervised learning, on the other hand, acts like a structural explorer for raw data. It doesn't have an answer key. It just wanders into the numerical wilderness and says, hey, I found a pattern here.
Moving right along to Section 2, clustering with k-means, grouping the online store.
So, going back to our online store vignette, let's say you want to naturally group your customers based on their monthly spending and website visits, so you're letting the data speak for itself. To do this, we use k-means clustering. And to really understand k-means, you have to understand its heart, which is the centroid. You can kind of think of a centroid as the physical center of gravity for a natural group of data points. It's calculated by literally taking the mathematical average of the x values and the y values of all the points assigned to that specific cluster. It is the anchor that holds a cluster together.
The k-means algorithm itself is wonderfully elegant. Step 1, we explicitly choose k, which is the number of clusters. Now, the machine does not decide k. We have to tell it, say k equals 2 or k equals 3 before the training even begins. Then we assign data points to the nearest centroid. Next, we recalculate the centroid's position based on those newly assigned points. And finally, we just repeat this process until the centroids stop moving, basically until they become stable. But you might be wondering, how exactly does it know which centroid is nearest?
Well, to answer that, we have to look at the math. Let's pull up some concrete numbers here. Imagine customer A has a monthly spending of $100 and 2 website visits. We also have a hypothetical centroid currently sitting at a spending value of $120 and 3 visits. The algorithm needs to figure out exactly how far customer A is from this centroid to decide if they belong in this group.
It does this using the Euclidean distance formula. Let's break this down together. It's actually pretty straightforward. D represents our distance. Our customer point is x1, y1. Our centroid point is x2, y2. The formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So let's plug in our numbers. 120 minus 100 is 20. 20 squared is 400. Then 3 minus 2 is 1. 1 squared is just 1. We add 400 plus 1 to get 401. Now we just take the square root of 401. And boom, that gives us the concrete numerical distance of approximately 20.02 between customer A and that centroid. This brilliantly illustrates the math in action. The algorithm is doing this exact calculation for every single data point and every single centroid, over and over, constantly shifting until every single customer is assigned to their absolute closest center of gravity.
Let's move to Section 3, dimensionality reduction via PCA, simplifying features.
Okay, I want you to imagine a complex data set, bloated with, let's say, 300 overlapping features. Customer age, income, spending, discount rate, time on site. It's just a massive, noisy hairball of data. We need to simplify this without losing crucial information, which PCA achieves by hunting for variance. Variance is simply a measure of how spread out your values are. Look at it this way. If everyone in your dataset is exactly 30 years old, the variance is 0. There's literally no useful information there to separate your customers. But if ages range from 18 to 80, the variance is high. PCA constantly looks for the directions or the axes in the data that have the absolute highest variance, because that widest spread is where the most valuable structural information lives. Let's look at exactly how PCA mathematically creates these new directions, which we call principal components. We're looking at a linear combination formula here.
PC1 is our brand new component. The X variables, those are our original features, like spending or visits. But pay close attention to the A variables. Those are the weights. PCA assigns these weights to tell us exactly how much each original feature contributes to the new component. For instance, it might heavily weight spending and visits together to create a brand new, synthesized feature that essentially represents overall engagement.
Now, we really need to address a major misconception here, and this requires looking at the outputs side by side. Compare k-means directly with PCA. K-means gives us a direct cluster assignment. It confidently says customer A belongs in cluster 0. It gives us a final grouping. PCA absolutely does not do this. PCA's output is simply transformed features. It takes 50 original features and squashes them down into, say, 2 brand new principal components, PC1 and PC2.
Listen, this is absolutely crucial to remember. PCA is not a crystal ball that predicts a final answer. It will not tell you if a customer is fraud or not fraud. It's not going to assign a class label, and it won't assign a cluster. It is fundamentally a pre-processing step. It just simplifies and cleans up the data by creating new, compressed features that we can later feed into other models.
All right, Section 4, Catching Anomalies, Flagging Suspicious Behavior.
Let's completely switch scenarios. Say you're a bank, and millions of transactions flow through your servers every single hour. Now, most are perfectly normal, right? Buying coffee, paying rent, but a tiny, tiny fraction are completely bizarre, unusual behaviors that might indicate fraud. So how do we find that needle in a massive haystack of numbers? Isolation Forest does this by utilizing a brilliant concept called path length. Think of this like a physical analogy. Imagine a really dense forest of data points. If you want to isolate a tree right in the middle of that forest, you have to chop through a lot of surrounding trees. But if a tree is standing way out in a field all by itself, an outlier, it takes very few cuts to isolate it. Path length is simply the number of random splits or cuts needed to isolate a specific data point.
Notice how this plays out across multiple decision trees here. We have point A, which is a massive, highly unusual transaction of $950. Across 5 randomized trees, it was isolated in 2, 3, 2, 4, and 3 splits. Super fast. Now look at point B, a totally normal transaction of $22. Because it's surrounded by thousands of similar normal transactions, it took 7, 8, 6, 7, and 9 splits to finally isolate.
Let's do the math on point A. If we add 2 plus 3 plus 2 plus 4 plus 3, which is 14, and then divide by 5, we get an average path length of just 2.8. Meanwhile, our normal transaction averages out to a much higher 7.4. This proves mathematically that the anomaly is isolated much, much faster than a normal data point.
Systems like scikit-learn use this precise math to assign a final anomaly score. A short average path length means the point is highly unusual, so it gets flagged as an anomaly, often represented by a score of -1. A long average path length means the point is deeply embedded in normal behavior, so it gets a score of +1. And this is exactly what allows a bank to automatically flag those short path transactions for human review. Finally, Section 5, Putting the Tools Together, the ML Toolbelt Workflow. Because the reality of data science is that you rarely, if ever, use just one tool in isolation. I want you to think about this question. How do these mathematical algorithms, these Euclidean distance formulas and variance weights, actually stack together in a real-world, production-ready pipeline? Well, here is an incredibly powerful classic workflow. You start with 100 raw, noisy features. Maybe it's complex user telemetry data. First, you use PCA. PCA calculates the variance, applies its weights, and neatly compresses those 100 features down to just 10 robust principal components, completely stripping out the noise. Then, you take those 10 clean components and feed them directly into k-means. K-means calculates the Euclidean distances and beautifully assigns the data into clean, separated clusters. PCA did the heavy lifting prep work, and k-means delivered the final grouping, a perfect 1-2 punch. But we must remember the golden rule of unsupervised learning. The machine is absolutely incredible at calculating distances, finding variance, and counting path lengths. It discovers the numerical structure flawlessly. But k-means doesn't have a clue what cluster 0 actually means for your business. It takes a human to look at that cluster, analyze the traits, and realize, okay, these are our high-value, loyal customers. Human interpretation is the essential final step. We've covered a ton of ground today, from centroids and Euclidean distance to principal components and path links. You now have an incredibly solid math-grounded tool belt for unsupervised machine learning. So I leave you with this to ponder. Armed with these tools that can automatically uncover invisible patterns, what unknown structures, what hidden stories are sitting silently in your unlabeled data right now, just waiting to be discovered? Thanks so much for joining me on this explainer. I'll see you next time.